A mass weighing 32 pounds is attached to a spring and allowed to come to rest at equilibrium. The spring constant is 5 pounds per foot and the damping constant is 2 pound-seconds per foot. At time t equals 0, an external force of 3 cosine 4t pounds is applied to the spring where down is the positive direction. Find the displacement of the mass as a function of time. Notice that this problem uses US units. This is important because the mass of the object isn't given, only its weight. So we have to calculate its mass using the fact that the force due to gravity equals mg. So since 32 pounds is the magnitude of the force due to gravity, 32 equals the mass times 32 feet per second squared. So the mass is 32 pounds divided by 32 feet per second squared, which is 1 slug. We are given that K equals 5 and C equals 2, and also told about an external force, F equals 3 cosine of 4t. The mass isn't initially displaced or released with any initial velocity, so y of 0 equals y prime of 0 equals 0. Putting all of this together, our initial value problem is y double prime plus 2y prime plus 5y equals 3 cosine of 4t, where y of 0 equals 0 and y prime of 0 equals 0. Unlike all the other examples we've looked at so far this week, this differential equation is non-homogeneous, so we'll have to break this problem into multiple stages. Start by finding the complementary solution, then find a particular solution, and then apply the initial conditions. The complementary equation is y double prime plus 2y prime plus 5y equals 0, and as usual, I'll let you practice finding the complementary solution yourself. Press pause and then play when you're ready. The complementary solution is yc equals c1 e to the negative t sine of 2t plus c2 e to the negative t cosine of 2t. This system is underdamped. Now we need a particular solution. Looking at the equation y double prime plus 2y prime plus 5y equals 3 cosine of 4t, what technique do you think we should use? We have method of undetermined coefficients, reduction of order, and variation of parameters. No matter what method you were thinking of using, it will work. This equation is set up to work great with any of the three methods, so you can just use your favorite. I'd argue, though, that the method of undetermined coefficients is the easiest, so I'm going to use that to find a particular solution. Second question for you. To use the method of undetermined coefficients, we need a guess function. What should our guess function be in this case? Hopefully you said something along the lines of yp equals a sine of 4t plus b cosine of 4t. Notice that this doesn't overlap the complementary solution at all, so we don't need to include an extra factor of t. This is another great opportunity for you to review material from Chapter 5. Press pause, use the method of undetermined coefficients to find a particular solution, and press play when you're ready. I'll write the steps down, but won't narrate them, so if you get a different answer, you can compare your work to mine and send me any questions. Yp equals 24 over 185 sine of 4t minus 33 over 185 cosine of 4t. Now that we have our complementary solution and a particular solution, we can put them together to get the general solution. Y equals 24 over 185 sine of 4t minus 33 over 185 cosine of 4t plus c1 e to the negative t sine of 2t plus c2 e to the negative t cosine of 2t. Before we find the values of the arbitrary constants, notice that if we let t approach infinity, the amplitudes of the sine and cosine functions from the particular solution don't change, and the complementary solution goes to 0. So over time, only the particular solution matters. For this reason, the particular solution portion of the function is called the steady state term, and the complementary solution is called the transient term. Also notice that even though we can't find the arbitrary constants until we have the full general solution, the initial conditions have no impact on the steady state term. Basically, the oscillations caused by any initial displacement or velocity die off due to the damping, leaving only the effect of the driving force. Again, I'll let you practice applying the initial conditions to find C1 and C2, so pause the video and press play when you're ready. C1 is negative 63 over 370, C2 is 33 over 185, so y is 24 over 185 sine of 4t minus 33 over 185 cosine 4t minus 63 over 370 e to the negative t sine of 2t plus 33 over 185 e to the negative t cosine 2t. If you chose to write your coefficients as rounded decimals, that's fine too. Now you might be wondering why we call the particular solution the steady state term and the complementary solution the transient term, even though each is made up of multiple terms. We've already seen that it's possible to combine sine and cosine terms of the same angle into a single cosine or sine function. So we could do this here to get a final answer that is made up of only two terms. If you're interested in this, keep watching. If not, our answer with 4 terms is perfectly good. For the particular solution, we need to combine 24 over 185 sine of 4t and negative 33 over 185 cosine of 4t. The amplitude c is the square root of a squared plus b squared, which will be the square root of 24 over 185 squared plus negative 33 over 185 squared, which equals the square root of 1665 over 185, or 3 square root 185 over 185. The sine of phi1 is negative a over c, which equals negative 24 over 185 times 185 over 3 square root of 185, which equals negative 8 over the square root of 185. The cosine of phi1 is b over c, so negative 33 over 185 times 185 over 3 square root 185, which equals negative 11 over the square root of 185. Since both the sine and cosine of phi1 are negative, phi1 is in quadrant 3. So no matter what inverse trig function we use, we're going to have to adjust the result to get the correct angle. I'm just going to use the inverse sign, so phi1 is going to be pi minus the inverse sign of negative 8 over the square root of 185, which is approximately 3.77. So the steady state term simplifies to yp equals 3 square root 185 over 185 cosine of 4t plus 3.77, or approximately 0.22 cosine of 4t plus 3.77. Repeating the same process for the complementary solution, we need to combine negative 63 over 370 sine of 2t and 33 over 185 cosine of 2t. And we'll just need to remember to put the factor of e to the negative t back in when we're done. The amplitude d equals the square root of negative 63 over 370 squared plus 33 over 185 squared, which equals square root of 8,325 over 370, or 15 square root of 37 over 370, or 3 square root of 37 over 74. The sine of phi 2 will be 63 over 370 times 74 over 3 square root of 37, which is 21 over 5 square root of 37. And the cosine of phi 2 will be 33 over 185 times 74 over 3 square root of 37, which is 22 over 5 square root of 37. Since both the sine and cosine are positive, phi 2 is in quadrant 1, so phi 2 can be calculated as just the inverse sine of 21 over 5 square root of 37, which is approximately 0.94. So the transient term simplifies to yc equals 3 square root of 37 over 74 times e to the negative t cosine of 2t plus 0.94, which is approximately 0.25 e to the negative t cosine of 2t plus 0.94. All of this work allows us to write the formula for the displacement of the mass as y equals 0.22 cosine 4t plus 3.77 plus 0.25 e to the negative t cosine of 2t plus 0.94.